All right, let's dive in. You've definitely seen one of these before, right? Maybe in an old grandfather clock or in science class. But did you realize that this simple swinging object helped us measure time, detect earthquakes, and even weigh the entire Earth? Yeah, today we're unlocking the secrets of the simple pendulum.
So, think about it for a second. On one hand, you have the delicate, precise art of keeping time. On the other, the raw power of geology and the just mind-bending scale of measuring a whole planet. What in the world could a single, simple object have to do with all three?
Believe it or not, the answer is hidden in this steady, predictable swing. Just a weight on a string, going back and forth. It seems almost too simple to be that important, doesn't it? But, as we're about to find out, that very simplicity is what makes it so incredibly powerful.
To really get how this thing works, we're going to build one, in our minds. We need to break down the parts and see exactly what makes it tick.
Now, to understand the physics, we have to imagine the perfect pendulum. It all starts with a pivot point up top that's completely fixed and has zero friction. Then you've got the string, it has to have no mass, and it can't stretch at all. And finally, at the end, a concentrated mass we call the bob. These ideal, perfect conditions help us zero in on the core principles at play here.
So, we've got our pendulum. Now what? Well, the most important piece of information we can get from it is actually hidden in the timing of its swing. Let's take a look at how we measure that.
The key measurement here is called the period, and we usually just write it as a capital T. Now, this isn't just the time it takes to swing one way. A period is the time for one complete round trip. So, from the start, all the way to the other side, and then all the way back to where it began. That full cycle, that's one period.
Trying to time just one swing with a stopwatch is super tricky. Your own reaction time can totally throw off the result. So here's a little pro tip. To be way more accurate, we time a bunch of swings, say 10 or 20, and then just divide the total time by the number of swings. It's a simple trick, but it really minimizes the error.
For example, if we time 10 full swings and our stopwatch reads 20 seconds, we just do the math, right? 20 seconds divided by 10 swings, that gives us a period of exactly 2 seconds. Simple.
Okay, this is where it gets really fascinating. We're going to start messing with our pendulum. We'll change the components one by one to see what actually affects the period. And promise you, some of the results are not at all what you'd intuitively expect.
All right, first up, the weight. If we swap out a light bob for a really heavy one, what do you think is going to happen to the timing of the swing? Does more weight mean a faster swing? What's your gut feeling?
And here's our first big surprise. The answer is nope. The mass of the bob makes no difference whatsoever. A 1 kilogram bob and a 10 kilogram bob will swing back and forth in the exact same amount of time, as long as the string length is the same. How wild is that?
Okay, so mass is out. What about the starting position? If we pull the pendulum back just a little bit versus pulling it way back for a huge dramatic swing, is that going to change the period? Now here's another counterintuitive result. As long as we keep the swing relatively small, we're talking less than about 15 degrees, the release angle has virtually no effect. A tiny swing and a slightly bigger swing take the same amount of time. This property of consistent timing is called isochronism, and it's exactly what made pendulums a total game changer for building accurate clocks.
So if it's not the mass and it's not the release angle, what's left? There's one big variable we haven't tested yet. What happens when we change the length of the string itself?
And this is the secret. The length of the pendulum is the single most important factor that determines its period. A longer string means a slower, longer period, while a shorter string means a faster, shorter period. So if you want to change the timing of a pendulum, you change its length. So, to just summarize everything we've found, the two things that matter are the length of the string and the strength of gravity. And the two things that don't, for our purposes, are the mass of the bob and the size of the swing. That's pretty much the whole story.
So why is this so important? This simple, predictable relationship isn't just a neat party trick. It fundamentally changed science and technology. Let's explore some of its incredible real-world applications.
Because the period depends so reliably on just length and gravity, it became the beating heart of accurate clocks for centuries. But then scientists flipped the idea around. If you build a pendulum with a precise length and measure its period, you can calculate the local force of gravity. This even let them detect things like dense ore deposits underground. And in early seismometers, a heavy pendulum would remain still due to inertia while the earth shook around it. A pen attached to the bob would then trace the earthquake's vibrations onto a moving scroll of paper.
And that really says it all. What looks like just a swinging weight is actually one of the most important instruments in the history of physics. Its deceptive simplicity unlocked our ability to measure the world with a precision never before imagined.
So we've seen how a simple pendulum could do everything from keep perfect time to measure the gravity of a planet. It really makes you wonder, what other extraordinary secrets are hiding in the simple physics of our everyday world?